Hello. So, as you can see, during my life, I've been wearing quite different hats, but they all brought me where I am now. So, I'm first and foremost an experimental music composer and electronic music producer. I also create sensor-based multimedia installations. I'm right now a PhD researcher in immersive audio and brain-computer musical interfaces. I'm not like a proper coder, but I use creative coding as a tool to create art. Um, I worked quite a lot as sound engineer and also acoustic consultant in Italy. So I had very much hands-on experience of how sound behaves uh, in the real world. And now I transferred these knowledge into virtual architectural acoustics. So I'm doing quite a lot of testings of architectural acoustics in a real engine. And I'm also a trained philosopher, Hermetic philosophy, Platonic philosophy, and continental philosophy. So everything I do is very much informed by that mindset. So today I'm going to show you how I went from creating music with plants to creating music with brains. Then I show you why brain-computer musical interfaces matter and how you can use them to generate music. The brain-computer interfaces foundations, so theory, application, and devices. I'm going to show you the device I'm using now, and you'll get to know that you can use it as well, because there is like a free program where you can test it. Then we get to BCI's architecture, and at least the case study that is Braino, my framework that I'm using for a VR installation called Emotional Music of the Spheres. And then we get to the conclusion. So I said, I'm very glad that I'm coming after you, because the mental process that brought me here was pretty much the same. So I started with normal classical composition. That is where you have complete control of what you are creating. You create every single note, you create all the sounds, you create how the sound behaves and how it's developed throughout time. Then I started to search for some more like freedom in the machine. So I started working with generative systems, auto-generative systems, um, modular synthesizers, a lot of modulations coming from the computer to the modular synthesizer and that. But while you are using even chaotic systems inside the machine, is still code. It's still deterministic in some way. So I wanted to have more freedom. So I started thinking how to connect the real world with the machine. I started generating music and art from there. So I started using sensors, making music with plants, generative art with various kind of sensors, temperature sensors, movement sensors, and things like that. And then from there, now I moved from composition as interaction to composition as system design. So now I'm trying to design complete auto-generative systems. So I started making music with plants with this module for Eurorack synthesizer, where I have a sensor that can be connected to anything alive, really, to plants and skins, to my dogs. And the biofeedback data gets transformed into CV and gate electrical signals that can be read by the modular synthesizer. So I started making music with this. You can find some of my videos on YouTube. The secret auto-generative music of plants and of mushrooms. Once I had, because I love mushrooms, they're really nice, like living beings. So I had a bucket of oyster mushrooms, and I started making music with them and also with plants. Sorry? Oh no, this is like the photo is real, but it's AI generated. Yeah, they grow like that, but not that quickly. um, the other one is an installation I did for the Aberdeen's Music Hall. I filled the music hall with a lot of sensors, temperature sensor, movement sensors, just like cheap webcams, and I programmed the movement sensing inside the touch designer. There were some microphones and some other sensors, and all the activity occurring there, and also the music that was being played inside the music hall was generating this digital painting on the main screen in the in the entrance. And then from there, I started thinking at how to generate music from my brainwaves, really, because one day I got extremely frustrated because I couldn't find the right music for my mental state in that moment. So I started thinking, okay, how do I fix this? Because I have to do something else. I cannot create the music I want to hear in this moment. So I said, okay, my mental state is something that I can measure. I can transform into numbers. It's data I can transform into numbers, and then I can transform these numbers into music. So I started researching. I'm not a neuroscience, of course, so I started from scratch completely. And I also didn't have money to buy a proper EEG device, but I had an Arduino on board. So I started researching, and I found out this Bitalino EEG chip. I got it, did some soldering, connected the cables with the sensors to it, and it was working. So I did some very basic EEG analysis in processing, just getting the beta and gamma, no, it was alpha and beta activity and overall signal activity in processing, send it over to pure data via OSC to generate music, and some visuals in Touch Designer. And I created this EEG-based quadrophonic installation that was the final project of my master's in Sonic Arts, final project. Then I started my PhD at the Aberdeen University in immersive audio and brain-computer musical interfaces. The question here was really, am I really just going to do some immersive audio installation? Is that just really it, the immersion, or is something that goes beyond a technology that makes you feel something realistic? So I started thinking, because of my philosophical background, how to look at the relationship between the subject, the listener, the user, the observer of the work of art, and the work of art itself. In the classical modern aesthetic theory, you have a subject that is looking at or listening to an object, the work of art that is there by itself, and it cannot be transformed, it can just be enjoyed in some ways. So I started researching on how to create a sort of feedback loops that would have the user generate the work of art. So the image below that is a particle system in VR generated in a real engine, and everything was generated by the EEG sensor I used for my master. In this architecture, I was using MaxMSP, and all the analysis made there, then sent the data over a real engine via OSC and generated particle systems and lights inside there, while the EEG generated music was generated in Max. So I had two softwares working together. The other image is a study on virtual architectural acoustics to try and find a way to generate realistic architectural acoustics in a real engine. In that case, I was using the Meta XR plugin for realistic audio. So why brain-computer musical interfaces? So this part is a bit complex, so sorry, bear with me. The fact that, I mean, now I'm not really showing you a finished product, but more of a framework, because I'm working on it as well right now as we speak. So this is the theory behind it. So why brain-computer musical interfaces? As I said, because I want to move from classical composition to process. So, you know, instead of writing for performance or writing music, I started writing for state of consciousness, if you wish. So BCMIs foundations, these are really not musical interfaces, but general brain-computer interfaces. So they rest on three pillars, of course. That is sensing the data, then data analysis, and then the interpretation of this data. And then you get the output from the interpretation that goes into the artistic part that can be anything from music to visuals. So yes, we sense electrical activity, in this case through EEG, but there are many other physiological sensors that we can use. We have ECG to sense the heartbeat, EMG to sense muscle activity. So it can be done with, yes, many different sensors. So the main part of brain-computer interfaces is the fact that our brain produces a constant bioelectrical signal that we can subdivide in these frequency bands. We have delta, that is deep sleep and unconscious restoration. We have theta, that is meditative or hypnagogic state. Alpha, relaxed wakefulness, and you usually get when you have eyes closed. Mu SMR rhythms that are very interesting to do some motor imagery, BCIs, we'll get to there later. We have beta, focused activity, tension, cognitive engagement, and we have gamma, that is integration, high-level processing. Of course, they are pretty much below auditory frequencies, and they increase in activity as much the brain activity increases, of course. So these are pretty much all the applications that you can have with brain-computer interfaces. Artistic and creative applications, generative composition, live performance control, immersive installation, biofeedback improvisation, neuroadaptive soundscapes for games and VR, therapeutic clinical applications, neurofeedback for self-regulation, rehabilitation post-stroke, cognitive training, sleep regulation, stress reduction, affective therapy. Human-computer interaction, attention monitoring in learning or simulator, or user state driving adaptive UIs. Research and experimental neuroscience, studying auditory motor coupling, emotion recognition, model training, neuromusical research. And then we get to the commercial consumer extensions, where you have apps for personalized meditation systems, wellness, and focus. So the hardware spectrum. We have, here you can see, well, the two types of the most used sensors that are the wet type and the dry type. The wet type uses gel, like conductive gel. So it's very good, of course, for conduction, but you can't really use that in a, let's say, an artistic setting, because it's messy and it takes a lot of time to set them up, like 20 minutes. With the dry electrode, if they are really good, of course, you get some latency, around 15 milliseconds, but they are good. You just put the headset on and it works fine. There are also dry metal pins, but they are like pierced through the skin, so they are not like really good. And then you get the like water saline sensors, but they are quite messy as well. They leave a sort of crust on the skin, so they're not good. So of course, the best choice for artistic purposes is the dry sensors. Then we have all the different type of headset, and they are like, they go from like the very cheap Arduino one to that is a G-Tech G Pangolin headset with 256 channels. So very high density EEG device. Some examples, these are not all the EEG devices you can find, but yeah, some examples. With Arduino, you can use the Bitalino EEG chip by Plux Biosignals. That is the one I was using for my first prototype. You have the ARD-EEG by PiEEG. There is an Arduino Uno Shield, and they also have a 3D printable headset. So on their shop, you can see many different things. And we have the AKEEG by StarCat. That is a shield for Arduino Due board. Then we have OpenBCI. I think that is the most famous do-it-yourself EEG device. This is just some examples of what you can find on their websites. You have various different boards, various different headsets, various different sensors. You can create your own EEG device. They have like a forum, a good community, a lot of information, so you can go there and create your own. Then we have the consumer wearable. You've probably seen some people using Muse, the previous one, I think, with Max MSP installations and things like that. They have their own app, and they are usually used for like relaxation training, attention training, things like that. I don't know if they're used for neurogaming as well, but yeah, it might be. And then we have the high-end medical grade. As you can see, that is a full head montage. It's called 1020. That is, the classic EEG device where you have all the cables coming out from your head, or something like that. That is a 64-channel membrane-trained mobile EEG. And also all the G-Tech stuff. And then we get to the interface I'm using. That is this one by Neuroconcise. Neuroconcise is a UK company that design medical-grade EEG headsets and analytic systems. And yes, I'm using one of these, of their headset. The good part is that they just don't only focus on clinical research, but they support and search for creative applications. So they have various different APIs that you can use. What I have is the main UIs is made in C sharp, but you can send the data via LSL, that is lab stream layer. That is the protocol that is usually used for biofeedback data connectivity. They have MATLAB API and Python. So they are very flexible. And the most important part is that their sensors can be used either dry or wet. So if you have time, if you are in a clinical situation, you can use the gel. While if you are in an artistic setting, an installation or whatever, you can use them dry, and they are very good, like very good connectivity. And this is also the new setting, and the pins are longer than they were before, and they are good for people with a lot of hairs, like me. The other one wasn't working that well because they were shorter. So this is a really good sensor. And also they have various different montages that can be used for various different things. You have one designed for neurofeedback, for visual evoked potentials. We'll see what is that. Motor imagery, and visual evoked potentials. So they also have developed tests that measure biosignals around the ear. So you have a lot of choice. And they are designing a lot of neurogaming apps. And they're very interested to this. So if you are a developer and you want to experiment with EEG and art generation, neurogaming, or whatever you can come up with, just write to him. He's the founder of Neuroconcise, or scan the QR code, or just ask me after this. So now that you know what you can use, let's see how you can use that. So the modes of brain-computer interaction. There are 3 different modes in which the brain can interact with the machine. The reactive one is where the user responds to external stimuli. This is where the steady state evoked potentials come in play. These are, you usually, have you ever played neurogames? Yeah, so you have like these flashing rhythm images that are recognized by the brain and are recognized by the EEG. So the EEG understand that the brain is reacting to something. So you can, for example, you are inside a game and you have to open a door. You put a flickering thing there. The brain enters in resonance with that flickering and generates a steady state evoked potential, and the door opens because the system recognizes that the user is looking at that. So this is reactive BCI, is reacting to external stimuli. Then we have active BCI. Active BCI is where the user actively tries to have the brain do something. For example, this is used with modular imagery. If you think that you want to move your right hand, the right move rhythm on your right hemisphere of the brain will go down. The machine responds to that. And for example, you can move a car that is going in that direction on the right. If you think at moving your left hand, the car would move on the left. So this is active BCI. This is just an example. You can do many different things once you get to know how your brain works and what you can do with that. Then we have passive BCI, that is the, let's say, probably the most common for music generation. The system monitors spontaneously the spontaneous brain activity. So you are there, and the system monitors your state in that moment, and the system reacts to that in various ways. This is used for emotionally adaptive music, for example, for affective computing, or just for monitoring. So, BCI analysis principles. So, of course, what you are getting from each sensor is a noisy signal. If we want to extract features from this signal, we have to analyze it. And there are various different ways to analyze it. Let's start with the spectral features. Using FFT analysis, you will get to have the brain activity based on the brain waves we've been seeing before. So you will have the brain activity of each brain wave, and that means something. For example, if you are relaxing, the alpha waves will go up, and the beta and gamma waves will go down. So from this, you can create a system that responds to this, of course. And the spectral features are usually used for neurofeedback, emotion tracking, and attention analysis. Then we have temporal features. They are peaks of signal in your brainwave activity. You have variations in time. They are called like evoked response, and they are called P300 and N400. These are some technical stuff, but basically you can set some thresholds on that and say, if this threshold is overcome, do something to the system. Then we have the steady state evoked potentials. As I was saying, is a periodic simulation of the brain. Something that I find really interesting is that the brain is a non-linear adaptive oscillator. That means if it's exposed to an oscillation, whether visual or acoustic, it starts oscillating with that frequency. So, and this is called neural entrainment, or steady state evoked potential. So the brain entrains to the rhythm. This is extremely interesting, and is also the reason why binaural beats work. Binaural beats are sonic beats that generate a third wave inside the brain. So let's say that you want the brain to go into relaxation, so to go into alpha state. You will need 8 hertz oscillation. How do you do that with sound? You cannot do that because it's below auditory level, 8 hertz, auditory frequency. But the brain does this. If you send 400 hertz of sine wave on one ear and 408 hertz of another sine wave in the other ear, the brain will do phase subtraction and will generate the 8 hertz oscillation at the center of the brain. And the brain will start entrain into that rhythm, and you will get into alpha wave. This is fantastic. I mean, think at what you can do with this. The brain is like, think about it as both analog to digital converter that generates both input and outputs. And you can do really whatever you like with this. And then we have the spatial and statistical features where you use short analysis for topography or dynamical features. So short analysis gives you the activity and the complexity of the signal. And you can also use this analysis to create patterns. Because you would have, for example, the most activity, where is happening the most activity on the brain is happening there, then there, then there. So you can create patterns that then you can map onto multidimensional spaces, for example, inside a musical machine learning algorithm. Machine learning. This is the worst part for me because I'm not a machine learning technician, so I'm still learning while I'm doing it. So from this part uses both external data sets. You can find many different emotion recognition data sets online, like Deep is one of them, and I'm using that, where you have your machine learning algorithm analyze it and extract the features that tells you at which brain activity corresponds which emotion, and then you can recognize them in real time with your headset. So at first we have feature extraction from EEG, time, frequencies, spatial domains, for example, alpha and beta power ratio that are indicators of arousal, frontal alpha symmetry, valence, short parameters for dynamical complexity, entropy, coherence, or hemispheric lateralization, I was saying before. If you want to move your right hand, something happens. So in this case, each frame becomes a vector. Then we enter into feature classification. We can use traditional ML, deep learning, dimensional models, categorical models. I quite a lot like the dimensional models because they can be mapped into dimensional spaces for sound. So they're really good. And then you have the final part of this system, that is the feedback and adaptation. So you have the prediction of emotion that then informs the system behavior. This is like the quite a simple BCI processing pipeline. You have the raw AG data, acquisition and pre-processing. You have, as I was saying before, you have to filter and remove the artifacts, remove the noise, remove the eye blinks and things like that. You have the feature extraction, where you analyze the signal and you get the data from there. You have the classification or detection, machine learning or statistical model, and then the control signal that generates the music and the visual. And then you have the feedback, because what is being generated changes the brain reaction. So you get to have, in the end, a closed, infinite feedback loop where what is generated transforms the brain, that then generates something else, and you go with this. And then we get to the audio mapping strategies. Again, it depends on what you want to do, but these are some examples of what you can do. So we have, sorry. So direct parameter mappings. This is very like the simplest one. Each EEG features control one audio parameter. So for example, alpha amplitude moves a filter cutoff, or beta power thickens the grain density of a granulator. Or you have the short parameters modulating modulation depth. Then we have multidimensional mapping, when features combine to define perceptual dimensions rather than single knobs. So you have a weighted mix of alpha and beta that might govern loudness, timbre, spatial positioning of the sound. And then we have the adaptive or affective mapping. As I was saying before, you can drive a MIR algorithm with this, and you can generate a certain genre of music based on the emotion of the person and of the user in that moment. Then we have generative machine learned mapping, uh, where I was saying before, EEG data could drive a neural synthesis model such as RAVE. So you would move inside a latent space of the machine learning algorithm with your brainwave activity. And then the symbolic or discrete mapping that is mostly used in reactive mappings, so with the steady state evoked potential. And of course, you can use all of them and create hybrid, super complex hybrid systems that can generate a lot of different things. So, case study. So Brino is the framework I'm working on, and because I'm quite bad at coding in C++, I'm using MaxMSP's Rambo. I don't know if you've ever used that. It's a add-on or library. It's a add-on of MaxMSP where you can code like in MaxMSP, but you don't really have the full functionalities, or like you cannot use libraries, external libraries inside Rambo, but you can use Gen inside it. And I'm doing the EEG analysis all inside there. And then I'm exporting the code into C++, and I'm importing it as a Real Engine plugin to have both the music and the visuals generated directly inside Unreal. Because we've been talking a lot about juice these days, you can do exactly the same. You just remove Unreal and put juice inside there, and then you create BSTs, you can create standalone applications coding in juice. And also Valerius libraries for descriptors analysis in C++ would come handy to do some descriptor analysis. So thank you. Because I'm going to use that. I was doing it in Rambo with the, the code block. But so I was about to start doing it in Gen, but I'm going to use your libraries in C++ directly. So this is the brain architecture. I'm getting the raw neuroconcise data, low pass, high pass filtering, of course, to remove all the electromagnetic noise. Then FFT analysis on the H channel is a 8-channel. So I get matrix of 5 brain waves per 8 channels. I'm getting the electric highest activity to have the trajectories to drive the Rave machine learning algorithm, brainwaves activity average that goes into the short analysis to get activity mobility complexity, and into musical gestures to do like various different things. I have the part with the affective analysis database, and some steady-state evoked potentials. This is the montage I'm using, and that is part of the user interface in Max, where I can see the activity of each sensor, and so I can create patterns. This framework I will be using with this VR installation in a real engine called the motion of the spheres. The hermetic literature told us that every planetary sky in the Aristotelian cosmos has certain correspondences. So let's do just very quickly and simple example. Venus is the planet of love, and the color correspondence is green. So I want to use these correspondences to drive certain system response based on the user activity. And on the contrary, if the user wants to go into a certain state, emotional state, they can choose on which planet to go to enter in that specific state. And I'm doing this installation entirely in Unreal Engine, not using external Macs, running together with Unreal Engine. As I said, the Rambo framework will be completely inside Unreal Engine. All the neural data drives adaptive music. I was using meta sounds, but I want to try and use your system because, yeah, it can be really interesting. And for the audio spatialization, this time I'm going to test the Atmogi hyper-realistic spatial audio. I've been testing, I think, every spatial audio plugin inside Unreal. This is just the one I missed, so I'm going to use that as well. And the system will be hopefully completely auto-generative. So the user will be staying inside a virtual space completely generated by their emotional state in that moment. Because I think that we have to use machines in a way that the human still remains at the center of the system, and not just remove the human and let the machine do the fun part. The machine are doing art now. Let's use machine like a filter, a framework to generate art by ourselves, for ourselves. So, thank you.